All right, now let's talk about everybody's favorite part, the complexity theory. Okay, so P, NP, NP complete. And I'm not going to include discussion of the approximation concepts here because we've just done that in the class. And so I'm assuming that if you want to know about approximation concepts, you can watch the videos that I just gave you. All right, so a polynomial time algorithm is one which runs polytime algorithm runs in big O of n to the d time for some d. All right, some d less than infinity. Okay, that's going to be our operating definition of a polynomial time algorithm. Okay, so this includes stuff that's, there we go, I knew that was coming. This includes algorithms that have log factors, right? So it doesn't have to be a strict polynomial for us to call it polynomial time. It just has to be big O of some polynomial. Okay, so that's one important definition. Another important definition is a decision problem. So a decision problem is a problem that has a yes or a no answer. Okay, so is there an assignment of Boolean variables that makes this Boolean expression true? That's a yes or a no answer. Right? Is there a way of traversing this graph that visits every vertex exactly once and returns to the start? There's a yes or a no answer. Right? So that's the kind of thing we're talking about when we talk about decision problems. Just yes or no. Okay, and so P is the class of decision problems that have polynomial time algorithms for solving them from scratch. So class of decision problems, DEC probs with polynomial time algorithms. And specifically, I'm going to make the statement for solving from scratch. Okay, so for solving from scratch. Okay, some examples. So checking if an array is sorted. If array is sorted. Checking if a number is prime. The decision versions of most of the problems we've looked at. Is this spanning tree a minimum spanning tree? Right? Is the given tree an MST? All right, that sort of thing. Okay, now NP is a slightly more complicated object, a little bit harder to think about. It's not an obvious class of problems, by the way. This is something that we discovered was an interesting class of problems early in the 20th century when people were starting to think about how do you formalize this stuff. So if you feel like NP isn't intuitively important, that's fine. But it turns out it is very important, a very important way to think about the problems. And so you need to kind of get your intuition to the point where you can understand what NP is doing, right? And it's just going to be a matter of training yourself to know what this definition means. Think about it, chew on it, and understand it. So this is the class of decision problems that also have a certain kind of polynomial algorithm, but it's not an algorithm that solves them from scratch. So class of decision problems whose correct answers, come on, pen, there you are, answers can be verified in polynomial time. Okay, so these have polynomial time verifiers, but they need not have polynomial time algorithms that solve them from scratch. Okay, and so one way you could think about this is that classes or problems in NP have algorithms that work like this. They are the world's luckiest guesser, and if the answer is yes, they'll always figure out how to get it right. Okay, that's the kind of thing that's one way you can think of an NP complete. An NP problem. So an NP complete problem then is our notion of the hardest problems in NP. So 1, it has to be in NP. Whoops. In NP. And then 2, if it's solvable from scratch in polynomial time, then so are all the other problems in P. In polynomial time, then so are all other problems in NP. Okay, and if this definition looks different from the one I gave in class, that's because it is. But this is really like the guts of the definition of NP complete. Like this is the notion by which we say these are the hardest problems in NP. That something about them means that if I can get an answer to this problem, if I can get an algorithm that solves this problem from scratch in polynomial time, then somehow that gives me for free an algorithm that solves all problems in NP in polynomial time. Okay, and the way we do this, the way we actually kind of formalize this, is by the notion of a polynomial time problem reduction. And I discussed that at least 2 times in lectures, so I encourage you to go back and dig into exactly what those means. All right, and then one final definition. I don't remember how often I use this in class, but the final definition is tractable. And tractable means kind of in just the lingo of people, it means that we can solve it. And so in this class, we're going to use the word tractable to mean solvable in polynomial time. Solvable in polynomial time. So for example, all problems in P are tractable, right? That's close to the definition of P. It's not quite, because tractable, you could be not a decision problem and also be tractable. But anyway, problems in P are all tractable. So here's the main question. Is P equal to NP? In other words, are the hardest problems in NP, in other words, the NP complete problems, are those problems solvable in polynomial time? And so basically what this is asking is, if you can check solutions fast, does this mean that you can also solve problems from scratch fast? And intuitively you might say, no, it doesn't. I don't see any particular reason why that would be the case. And yet, mysteriously, we still don't know the answer. This is a major open question. So there's 2 possible worlds, and I'll draw the classic pictures. 2 possible worlds. So either, here's our class NP. Either the NP complete problems are kind of distinct from the P problems, or they coincide with P. So here's all of NP, and so that means this is the other version of the world, is that P equals NP, which equals NP complete. Okay, so this is the world where P does not equal NP. This is the world, by the way, on the left, the world that we are conjectured by most people to live in, probably our world. And then this is the world where P equals NP. And the stunning thing about a world where P equals NP is that all problems in NP have polynomial time algorithms, right? That NP complete problems all collapse down to simple problems, right? They're not difficult to solve. All right, so I gave you a final review sheet. If you're some random person watching on YouTube, I apologize, you don't have access to this sheet. But if you're actually registered for this course, you have access to the sheet. And I gave you some questions here. And so here's a couple questions that I'll go through, and I'll kind of talk about the intuitions of these as we're going through them. All right, here's how we're going to do this. So there's a list of questions. So let's say question I is every problem in NP is intractable. Oh, I need to give myself a tiny bit more space here. There we go. Every problem in NP is intractable. All right, I'll tell you exactly why I include this problem. Because a lot of people leave this course and inexplicably, I cannot for the life of me understand where they would get this idea, because I tell them again and again and again this is not the case, but they get this idea that NP is the class of hard-to-solve problems. That's completely and utterly, totally contravening the definition of NP. NP is the class of problems that have polynomial time verifiers. All problems in P are also in NP, right? Look at the Venn diagram, right? P here is completely contained within NP. So please never, ever, ever fall into this trap of thinking that NP means hard, okay? And so I put this in here to try to catch these people. And now I do two things. I say, so now suppose P equals NP. Now what's the answer? And suppose P does not equal NP. What's the answer? All right, well, if P equals NP, then we know that actually all problems in NP are tractable. So then the answer here is no, right? So in fact, the opposite of this is true. If P equals NP, all problems would be tractable. If P does not equal NP, then the answer is still no, because NP does not mean hard all by itself. NP just means it has a polynomial time verifier. And so the answer here is no, and the reason is that NP contains all P problems, right? It contains a vast number of tractable problems, even if P does not equal NP, okay? So now let's go down here to part 2. So part 2 says the hardest problems in NP are intractable. Hardest problems in NP are intractable. Okay, if P equals NP, then the answer is no, because P equals NP means directly that the hardest problems in NP are tractable. Okay, so the answer here is no. If P does not equal NP, then the answer is yes, because P does not equal NP literally means, like the thing that it means is that the hardest problems in NP are intractable. Like that is equivalent to saying P does not equal NP. Okay? So part 3 says there exists a problem that's in both P and NP. In both P and NP. Well, this is true no matter what, because every problem in P is also in NP. So this is always true, no matter how the P versus NP problem gets resolved. Okay, and so now 4. I skipped one. This is actually 4 here. And now I am so happy I'm on a digital whiteboard because that makes it very, very easy. So 3 was a different problem. 3 says every problem in P is tractable. So every problem in P is tractable. Remember what our definition is for tractability. Tractable means solvable in polynomial time. P is the class of problems of decision problems that are solvable in polynomial time. So this is yes, regardless of how P versus NP is resolved. All right, now 5. 5 is another incisive one. So 5 asks, there exists a problem in NP, but not in P. Okay, so if P equals NP, then P and NP coincide. That's what P equals NP means. So the answer would be no. And if they're different, then yes. That's what being different means. Sorry. What? Sorry, I misread my sheet. Let me make sure that I'm answering this properly. So there exists a problem in NP, but not in P. You know what? I'm going to leave that right there, because that's fine. This is like 4. Let's call this 4.1. Okay, this is absolutely the correct way to answer this. There exists a problem in NP, but not in P. Isn't the case if P equals NP, and it is the case if P does not equal to NP, and that's because there's problems like, for example, here that are in NP but not in P, if they're different, if P and NP do not coincide. Okay, so now let's go on to the actual problem 5. So problem 5 says there exists a problem in NP, but not NP complete. All right, so if P and NP coincide, so if P equals NP, here, let me just remind you which ones of these are which. P does not equal NP. So if P equals NP, then the answer is no, because every problem in NP is NP complete if P equals NP. And if P does not equal NP, then the answer is yes, because then there are problems in NP that are not NP complete. For example, every problem in P. All right, on my sheet I say that these next two are kind of advanced, so let me write them out and then we'll think about it. So there exists a problem in NP, but neither in P nor NP complete. Nor NP complete. And it turns out the answer to this is kind of surprisingly weird. The answer is no if P equals NP, and that one's obvious, right? Because if P equals NP, then NP complete is also equal to P, and you have that they're all the same. On the other hand, over here, it turns out the answer here is yes, that there have to be intermediate problems if P and NP are distinct. All right, and then the last one is also a bit advanced, and so this one is about quantum. And I just mentioned this one day in lecture, so whether you remember it or not, this happened. But I say a physical quantum computer would resolve P versus NP. P versus NP. And if I ask a question like this on the exam, I'm gonna give you a free-form response. It's not gonna be this answer or that answer, because you really have to address some of the nuance here. So one of the really easy answers is no. Like, you could just say no, and as long as you justify it, that's fine. And here's why. Because we currently have physical quantum computers. They're very small. They're not useful for much at the moment, but they exist. Okay, so we have them, and the problem is still open, and so the answer in that case is no. Also, you could say maybe if P equals NP, maybe quantum computers could help us discover that, right? They could help. Having the computer would accelerate algorithm development, and then we could use these new algorithms to solve NP complete problems in polynomial time on quantum computers. Maybe. It's absolutely a maybe. Like, if you argued that correctly and coherently, then I would accept your answer. But the easiest answer on this one is no, because we already have quantum computers and the problem's not resolved. So that's the end of this. I'm going to go ahead and sign off. I've given you lots of review material here, and reach out to me if you have any questions.